Hi everyone and welcome to lecture 16 of Introduction to Computational Literary Analysis, and today we're going to look at topic modeling. All right, here we go. So topic modeling is a technique of text extraction, of text mining. And the idea is to find words that co-occur across documents, and these words tell us something about common themes, common topics, things that happen statistically more than once, in more than one document. I'm hesitating right now to come up with a really definitive answer to this, because it's more than just a text analysis technique. Of course, it's like a statistical technique that, given like any collection of objects, we could find similarities among all of the items in those collections and group them according to categories that seem semantically useful, so that show us commonalities between them. So I should show you a little bit of theoretical background behind common topic modeling techniques. So one of the most common ones is latent Dirichlet allocation. And it sounds fancy, but really, a Dirichlet model is just a model, like a Gaussian model, like a normal curve, or or a beta distribution. But in this case, what it does is it tries to find hidden, latent Dirichlet models of data that are within your data set. And it tries to infer these. And yeah, it's better if I show this to you, show you a little bit of background. So latent Dirichlet allocation was, it was invented by Dave Bly, one of my professors, and a number of others. And it's since come to be used across statistics as a statistical method, not just for text analysis, but for lots of things. Here's a really famous example where Bly and others, they run an LDA analysis on a collection of newspaper articles, and from the New York Times, and these are the so-called topics that are generated. In other words, a topic is a collection of words that co-occur in a certain way across documents. So so you can see there's kind of like a music topic here. There's kind of like a literature topic. This is kind of like an art, like a visual art topic, a sports topic over here. All of these, are correlated with you have politics, you have plays. All of these are correlated with each other across documents. So here's another explanation, graphical explanation of what LDA does. Another way of doing it is you can think about LDA as a way to infer topics from a model, given a concept, a model of the whole text as a mixture of proportions of various topics. So say for example you have a newspaper article that has to do with genetics, and it has to do with biology, and it has to do with neuroscience, and it has to do with computers to some degree. Well, if you say to the LDA model, hey, I want you to infer 4 topics from this article, it will probably find these topics because they are correlated with each other and they have these same correlations in other documents. And that's key, that what we're dealing with is always a collection of documents. And that's what makes topics meaningful. So let's play around with this. So here is kind of another graphical explanation of how topic modeling works. And a bit of a contrived one, but one that you can play around with a bit at this URL, lettier.com/project/LDA topic modeling. So the engine allows you to sort of generate contrived examples, and these are very contrived examples. So this one, for example, is 4 documents, and these documents contain words. I'm saying words very loosely, and these words are either star or cat emoji or top hat emoji. And you can imagine that real text are not like this at all. They have way more than 4 words. But if we run LDA on it, and if we tell it we have 3 topics here, and we can adjust these parameters. So so if you've taken a statistics course, you might know that certain models, certain statistical distributions have these parameters that control the distribution, or control or describe it, right? So you might have a parameter that says how high your bell curve is. You might have one that says how wide it is. And the same is true for Dirichlet models. You have alpha and beta parameters, and changing these will change what LDA is looking for and how it detects things. And often because you're running inference, if you give it a certain number of iterations, often the accuracy of what it's trying to predict improves after each iteration because it's a stochastic, or it's a random activity. So if I run LDA here, it tells me it thinks there are 3 topics, and the first topic, all topics contain all terms, but it says the first topic is mostly about stars, second topic is also mostly about stars, and the third topic is mostly about top hats. And cats actually most belongs to the first topic. So yeah, so it says first topic is cats and stars, second topic is stars, and the third topic is mostly top hats. So this is like a really contrived example, but if we were to write something more textual, this would make a little bit more sense. So I'm just going to write a few newsy sounding articles. I'm going to have some be about computers, and I'm going to have some be about sports. So computers are cool because they have disks. Actually, no, they have screens and disks and cables and stuff. Disks are important to computers with cables because computers also have screens. And then I can have another one, sports like running, jumping, and swimming happen in sporting events like the triathlon. And then triathlon athletes play sports like running and jumping. So you can see what it's done is it's created a count matrix of terms and documents. This is often called a document term matrix. So basically we're counting what terms appear in what documents because we're interested in knowing how these terms are distributed across documents, and from these distributions we're going to infer what topics they have in common. So now we run LDA on these documents, and it says it thinks there are three, but I've told it there are three documents, so let me change this to two. Now I'm going to run LDA again. Okay, and it says these are the top scoring ones in topic 0. It says, well, actually the top scoring ones are 0.07. So that's screens and stuff, and they, cables, and R. And over here, the high scoring ones are jumping, running, swimming, triathlon, just the stuff that I've repeated. So it basically has succeeded in my incredibly contrived example in detecting the two topics here, which are computer stuff and sports stuff. All right, so what's this going to look like when we start messing around with it in Python? Well, first I want to import a news corpus from NLTK corpus because it works really well on news articles, and this would be a good example to start with. For literary text, as you can imagine, what a topic might be is so much slippier as a concept, and so it's best if we start with something very concrete. So the Reuters corpus, is one that has lots of news articles. So what do we have? We have categorization. We have categories here. Let's see what that looks like. These are really odd categories. Barley. Yeah, what else can we do with this corpus? We can get paragraphs, we can get raw texts, we can get sentences, we can get words. Yeah, what if we get raw text categories equals barley? Okay. French free market cereal export bids detailed. So let's create a document term matrix of some of these. I wonder how many file IDs we have. We have a ton of news articles here. Yeah, why don't we get some from just a few categories? So why don't we try some that are different as a good starting point? Yeah, so how about gold and coconut and coffee? These should be different enough. So we want to get Reuters raw, and we're going to get Reuters Reuters raw for categories, and categories takes a list, I hope. So gold, coffee, and coconut. Yeah, well, that's 2 foods and 1 non-food. So why don't we make it something else? What about income? Gold, coffee, and income. And what is this going to give us? Now if we look at Reuters raw, it says Has a length of, it has a really long length. So it looks like this is just one long string, and that's not really what we want because it's kind of concatenated all of these things together. So instead, what we want is a text for each one. So we're going to give it one category. And that category is going to change depending on all of these things. So we're creating a list comprehension now where it's going to get the raw text for each category. I'm missing a parenthesis or something somewhere. Okay, there we go. Now if we look at the length of this, it says length 3. And so this is what we want. We want gold, coffee, and income. But we also want, we also want these to be separate documents. We want to have not just a few documents, but we want to have many of them. So, what if I split this up into gold, coffee, and income? Yeah, what if I looked at the length of gold? That looks pretty short, actually, but this is quite a lot. So we can break this up into several texts if we want, but I bet there's a built-in way of doing that in this corpus reader. So I bet we can get file IDs and spelled it wrong for some categories. So if I say categories equals gold on file IDs, it tells me here are all of the documents about gold. So maybe I can get 10 of these and 10 for coffee and 10 for income. Okay, so what I want to do is I want to get the raw text for certain file IDs, and I want to get certain file IDs from the categories. So I can rewrite this, say gold files, coffee files, income files, and I can get file IDs from these categories. And actually, why don't I just call this file names? So file names should be length 3. And then, so for each file name, for each list of file names, I'm going to get, say, like the first 10 of them, so I get 10 each. For each list of file names in this file names list. So, that should give me 10 file names for each category. And now I know I can get the raw text by saying, by running Reuters raw over that. Yeah, so why don't I, just do it this way. Gold file names, coffee file names, income file names. And then for each of those, I'm going to want to get the raw text from each one. Yeah, and in fact now I can replace this whole thing with like file names, and I can replace this with file names too. So I know this is going to get me the raw text for each file name, for each of the file names in each of these file IDs for all of these categories. So this is kind of convoluted, but um, maybe I can call this Reuters raw. Okay, now let's look at what Reuters raw is. This is a list of length 3, which is great. And what is the first one like? Okay, that's a string. Yeah, we still have one long string because it's, yeah, we're getting all of the file names here. So really what we want is separate documents. So we want to have 30 of them. All right, so I can make a list comprehension within a list comprehension. So here I'm getting the raw text for each file name in the list of file names that I get from this big list of file names. And this is what we want because Reuters raw should be 3. The first one is 124. That's because we're not getting, yeah, we're not getting the first 10. Great. Now we should have the first 10. Can I unpack it like this? I wonder if there's a way that I can concatenate all of these. Yeah, this isn't working quite how I thought. We can do it the long way. So right now we have a list of 3, but we want a list of 30. So we can just say Reuters docs equals a blank list, and we could say for collection in Reuters raw, because there are 3 of them, Reuters docs, we're going to append something to that collection, but we have to put this in a second for loop. So for doc and collection, Reuters docs append that doc. So now we should have a list of length 30. Wow, that was kind of harder than I thought it was going to be. All right, so we have now 30 documents, and these 30 documents represent 10 news articles from 10 different categories. The first 10 are gold, the second 10 are coffee, and the third 10 are income. So we have a pretty good corpus to start with that will behave nicely with latent Dirichlet allocation. So I want to import some of this stuff from sklearn. So latent Dirichlet allocation is in decomposition. And feature extraction .text has our module called count vectorizer. And so, yeah, note one thing here, we're not using the TF-IDF vectorizer because, as we've seen, the quirk behind latent Dirichlet allocation is that it likes to work with counts rather than frequencies. Okay, so we have a list of documents that now we can count vectorize. So I'll call this count vectorizer, and we can initialize our count vectorizer, and we can give it certain parameters. So one thing is we probably want to tell it to remove stop words. And that's because what we're dealing with topic modeling is we're trying to find statistical similarities between words that are not the most frequent words. So it's we are dealing with content and not style, and so we should remove stop words. So yeah, do we have documentation behind stop words, what this does? Okay, it says if we give it a string called English, it will just use the built-in stop words list for English. And what other parameters should we give it? Well, we do want to say that at minimum we are looking at words that appear in all documents. So yeah, let's try it like this with these default values. And we can give it our Reuters docs. We can call this Reuters counts if we want. I keep spelling it like it's a French word. Oh, right, I forgot. It's fit transform. Okay, so now we have a document term matrix. And if we wanted to, we could inspect this in an easier way by getting the feature names, so we could get word labels from count vectorizer by using get feature names. And yeah, we could get some kind of label for those documents. What does one document look like? Yeah, so we could use as a label, the first 50 characters of each. So we could say that a label is first 50 characters of each doc. Let's see what that is. Great, so these are pretty much the headlines. It's a little messy, but we get the idea. Okay, and we could inspect this further using pandas. First I have to come up here and import pandas as PD. And then down here I can say my data frame is those Reuters counts. But I'm going to make it dense, first of all. And then I'm going to say that, well, I'm going to look at that because I have to figure out what the shape is. So we're dealing with 1,271 terms and 30 rows. So the rows represent the documents. So I'm going to say the index is Reuters labels, and columns is word labels. Great. So this is just doing nothing else other than showing us the document term matrix here, which is just for each word, how many times does it occur in that document? So the word 000 occurs 2 times in this article, Western Mining to Open New Gold Mine in Australia. and the word year occurs once in this, and so on. And maybe it would be useful for us to get rid of all of these numbers. Yeah, where and how can we do that? Well, there are lots of ways that we could do that. One way is we could change the token pattern so that it doesn't find numbers. Another way is we could give it a custom vocabulary, so we could say only look at these words and have those words be not numbers. So we do actually have a vocabulary from this now because we have word labels. So if we were to get a subset of these word labels without all of the numbers, so word label for word label in word labels if that word label is alpha. And we could call that word labels no nums. Then we could change this so that our vocabulary, in other words, the words that we're looking for, is word labels no nums. And now we would need to fit and transform that again. I'm doing something that I shouldn't do, which is I'm writing this and rewriting some of the stuff that I've done before so that I could save myself some cutting and pasting. But I really shouldn't do that. So instead, yeah, I'm going to add that to the bottom of this. Yeah, so I'm going to copy this. I'm going to reinitialize that count vectorizer. And then I'm going to fit and transform it again down here. And then that can stay the same. And I'm going to redo this pandas data frame. Right, it says this index is not working because I'm actually giving it an old word labels. Great, so now you can see that the document term matrix is actually, we've removed the numbers successfully. Yeah, so I can set this to something like Reuters data frame in case I want to use that again. But that just, this is only just to help me visualize this right now. And maybe I want to do something with pandas with it later. But I already have the counts in this step. So that's really the thing that I need. Just like with PCA, I'm going to initialize a new model for latent Dirichlet allocation. And why don't I say that the number of components here is going to be 3. So this is the number of topics that it's looking for. And this is pretty important because, if you're looking for 3 topics, in our sense, we expect it to come up with the topic gold and, a topic for coffee and a topic for income, like a finance topic. But we could make this higher and it would find other topics as well. We have lots and lots of other things that control how this LDA is going to work. And we can read about these. There are lots and lots of papers written about all of these different methods. I think this will do for now. So if we fit and transform our Reuters counts using LDA, and I'm going to call this LDA out because I am not feeling creative today. Yeah, we have the same thing that we would expect from, say like the PCA out, but here we're dealing with a matrix of shape 30 and 3. So, yeah, we know again that this is 30 documents, and the percentage of each topic. But yeah, not that's not necessarily what's going to be the most semantically useful for us. Yeah, what if we were to look at this more visually, though? Because we should be able to see some affinities. Because the first 10 documents we know that's gold, and then we know this second 10 is coffee. We know the last one is income. Yeah, so it's doing an okay job because it definitely thinks that most of these documents belong to topic 0, which is probably income, like finance related stuff. And it thinks these middle topics also mostly belong to that topic, but some of them, like this one and this one, belong to topic 1, which is, this is probably coffee topic, and this is probably the gold topic. But gold and income have some similarities, and coffee and gold have some similarities, apparently. So it's interesting what it thinks are these topics, and this is going to be a lot more clear once we get the features, in other words, the words that it has detected here. So that's going to be in this LDA object. And it's one of these. I believe it's components. Yeah, so what is the shape of these components? Okay, yeah, so what we have here is a matrix of, we have our 3 topics, and this is our 1111 terms or words. Right, because word labels no nums. Let's look at how big that is. Yeah, actually, where do I define that? Over here. Yeah, 1111. So if we wanted to inspect this again more semantically, we could say, let's make a data frame of the LDA components. And the index or the rows is going to just be like topic 0, topic 1, topic 2. I also could have written this topic plus string of x for x in range 3. That's a bit of a contrived way of writing that, though, and not a whole lot more readable. Yeah, but our columns are going to be those word labels, no numbers in them. Let's look at that. So it tells us for each word how much it thinks it belongs to that given topic. So these are probabilities. So this says that the probability year is most likely to occur in the topic 0, which is kind of like, yeah, which topic is that? That's the finance topic. So what we want is a list of words for each topic that's going to be like the most common, the most probable words for that topic. So there's a way that we can slice that. Topic word matrix, we can call that. And now topic word matrix, if we get topic 0 out of it, and I'm spelling this wrong, Merix. And then if we sort those values, and we want to see the biggest ones up top, so we'll say ascending is false. Great. And then we're going to look at more than just the first 5. We're going to look at the top 15 or something. So topic 0, these are the words that belongs to topic 0 that it has inferred. So percentage, said, dollars, year, coffee, rose, billion, April, February, January, department. So this earnings, so this looks very finance related, but it's also coffee is in here. So does it, yeah, does it perfectly detect like a coffee topic? Not really, but this is kind of a finance topic of sorts. So let's repeat this. I'm just going to copy and paste this. Let's repeat this for topic 1. See what it thinks of the words in topic 1. Exchange, trading, coffee. So this is another kind of finance, and yeah, this is another sort of finance and commodities and exchange and trading topic. And the third one, gold deposits, year. Yeah, again, this is another of these kind of finance topics. So you can see what it's done is it hasn't really found gold, coffee, income. It's really found 3 collections of words that co-occur in kind of unusual ways. What if we were to use different categories here entirely? So what are the categories that we can choose from again? Let's look at them. Because are these all commodities of sorts? Because that's going to give us strange results. Yeah, okay, well, what if we tried a completely different thing? So we could instead get the brown corpus. Brown corpus might be better for this. And it has relatively the same API. So what if we said brown file IDs for the categories in, and here we're going to give it like very different things, fiction and romance. Actually, how about fiction, government, and reviews. Then I can reuse all of this code. Right, but except for Reuters raw, it's going to be brown raw. Yeah, and I'm removing the numbers again. I'm doing LDA on this again. I'm plotting this again. Okay, this is interesting. It thinks that there is barely anything from topic 1. Oh, so here I'm dealing with 9,000 words. That might be a little bit too much. Uh-oh. Yeah, this is part of speech tagged, so no wonder I'm getting crazy results because I'm dealing with parts of speech instead. So this is kind of like a lesson that for real I should pay attention to what it is that is the kind of data that I'm working with. What what is this? What are the word labels? That sounds right. What are the word labels? Actually, just what does one document look like? Right. So I don't want raw because this is already POS tagged. So maybe I want words instead, but let's join together. Should we join together those words? This is going to be pretty strange. Yeah, because we've effectively detokenized this. But yeah, this looks more regular. But yeah, in the count vectorizer, why don't we say that the max features is only like 1,000? Because if we give it too many, it's going to have to try to find too many correlations. Okay, this looks a little bit more sane. Okay, state, business, property, road, island. This is very clearly like a government type of topic to me. This one, like man said, Mr. Music Time did. This looks very much like a fiction topic to me. State, fiscal, tax, vehicles, years, Rayburn, towns, states. This looks like another government topic. So what do we have? Fiction, government, and reviews. So fiction, it thinks that fiction, government, and reviews, it thinks that fiction and reviews belong to the same topic. And then it thinks government actually belongs to two different topics. Topic 0 and topic 2. So this is like government topic 1, and this is government topic 2. So you can see it doesn't do a perfect job often. It behaves strangely. Sometimes that strange behavior is desirable, though. Sometimes you find these topics that are really exciting, because it shows you something that you can't quite put your finger on, but is a statistical phenomenon. In other words, we have groups of words that occur together statistically in a way that could lead us to a kind of literary critical argument. Um, if I want, I can take this chart that I'm making here, and I can do it again down here. But instead of 0, 1, and 2, I can label these. First, I need to know what is the shape of this. So the documents are the doc labels, but I won't add those. Instead, I'll just add the columns. And the columns are going to be, I'm going to give, I'm going to make, instead of topic 0, topic 1, and topic 2, I'm going to make useful names for these. So I know that I can do this to get the top 15 words of this topic. So what if I were to get the top 8 words of this topic, and then I were to call this something? So I'm just getting the index. Now I'm forcing that into a list. Great. So for a given topic name, I want to return that topic name from the topic word matrix to get the words. Great, so now I have labels. Actually, I'm going to join these together with a space. This is now the longest and craziest looking thing. And instead of 8, why don't I just do 5? And I can say, okay, I can call this topic labels words. Yeah, now let's see what that looks like. Great, and we can make that our columns. And this just gives us like a better idea of what this looks like. Maybe I can increase the size of this a little bit. Yeah, I'm going to make it a lot wider and not quite as tall. Great, so you can see fiction and reviews, it finds affinities within these. And for government documents, it thinks that fiscal and year and tax on vehicles, this is very much a financial government document. State business property, Rhode Island, it feels very much like a real estate government document. And both have the word state in them. So if we were to play around with the parameters of this, and by parameters I mean both of the count vectorizer, which is the preprocessor that really does the heavy lifting, and the LDA parameters, we would get slightly different results. So to do this, we would again be looking at things like max DF and min DF. So what if we said that we want words that occur in, at minimum, 5 of our 30 documents? We want max document frequency. We don't want words that occur in all of our documents. So we don't want 1.0, the default, which is 100%. And we don't want that because the words that occur in absolutely all of our documents are going to be, kind of stop words. They're going to be words that are just kind of part of the language and not part of the topic. So what if we were to say we want our maximum document frequency to be like 0.08? So or even 0.7. So 70%. So show us words that are that happen at minimum in 5 documents. So they must be somewhat common, right? So this will definitely find words that are common amongst the documents in that category. And this will find words that happen at most in 70% of all of the documents. And you'll see just how sensitive this analysis is to parameters like that. It's still more or less the same thing here. Let's let's compute these again. Oh wow, so medical and pathology, we have like a medical topic here now, so this has changed a little bit. It still thinks that reviews and fiction are pretty much the same thing, only now reviews contain this kind of medical area, this medical topic, and it still thinks that government documents are one of two things. They're either medical documents or they're kind of financial documents. What if we were to use completely different categories? Romance, religion, and hobbies. That's weird. I only have a total of 5 documents. How could that be? Because here I still have 30. Yeah, I better inspect some of these things to make sure I know what it is that I'm working with. Okay, yeah, that's right. So that's 30 documents, 981 columns. Oh wow, this is going to be interesting. So it finds commonalities between them just basically across the board. What if we were to really restrict this? What if we were to say, also the max features we want is like 1,000. Yeah, like 1,000. We're only looking at 1,000 words. Okay, yeah, now we start to see it's a little bit less noisy. What if we were to bring this down even more? Let's try 700. So we're only dealing with 700 words. Well, that's weird. Now it says 981. Yeah, maybe one of those parameters is overriding another. Still, this is less noisy than before, I think. Okay, so let's keep tweaking these parameters. What if I said, show me words that occur at maximum in 60% of all documents, but they can occur, so long as they occur in 3 documents at minimum, that's fine. That's actually a lot noisier. Yeah, let's see what these topics are. So one is man, church, Hanover, time, God. So this is definitely a religion topic. And we know that we have, if I go all the way to the top here, we know that we have romance, religion, and hobbies. So it kind of makes sense that religious words would appear in romance novels. So that's what's happening with the blue spikes here. So maybe these are kind of religious romances. And these are religious texts. But religious texts, yeah, so the second topic is said like God world class, which is also kind of like another religious topic. Used world spirit aircraft time is this green one. So this must be a hobbies thing, but it thinks that aircraft and world and spirit is a topic that is in religious documents and hobbies. You see, I find this fascinating because it doesn't split it up as cleanly as you think. It's giving us kind of the results that we don't really expect, but which are interesting nonetheless. And if I were to change the number of topics too, this will greatly change yeah, what it is that we get back. So if we are looking at 5 topics, what are those 5 topics going to be? Is that too many? Yeah, and I can use this thing down here. Okay, so it says that the religious texts are really all about this one topic, God, man, world, spirit, church, which makes sense. But in hobbies, it finds this aircraft, boat, new nuclear missile topic only in hobbies, but also it finds over here, said like man old did is the main topic for romance. But also you have kind of a religious topic for romance that appears. This Hanover like God said time appears in all 3. So let's see. So yeah, I've taken an hour with this so far, and I could go much longer actually, because tweaking these parameters, and again, the important parameters here are the number of topics you're looking for, the max number of features you're telling it to get, the vocabulary that you give it, the maximum number of documents or the maximum proportion of documents you want it to look for, the minimum number of documents that you want words to appear in, and probably even, even more of these parameters. All of the parameters that you put into this are going to be super important. So you can imagine topic modeling as like a really huge control panel where you can get extremely useful information about the types of topics that are in your collection of documents, but only if you, tweak these knobs just to the right level, that you start to find something semantically useful. So, yeah, this is an introduction to what you can do with topic modeling. Remember, it's not a magic solution. It's not something where you can drop a whole bunch of documents in and out come your results, and they're really fascinating results. Instead, it's something that you have to pay very close attention to, and you have to know your corpus at least somewhat ahead of time. And yeah, so one of the optional homework assignments is going to be to do one of these. And yeah, so my recommendation in that case would be to just play around with the parameters as much as you can until you find something that starts to sort of make sense. All right, that's it for today, and looking forward to chatting with you about this on Zulip.